Hello, everybody. Welcome back. My name is Lars Nilsson. I program for Austin Film Society, and this is yet another in our Science on Screen presentations, presented by, helpfully brought to us from our friends from Sloan Foundation and everyone else who works on the Science on Screen initiative. Now, this has been going on for a good while, and I really always enjoy watching films and having really smart people talk about the scientific concepts in the film, and that's what we're going to do today. So if you're one of those people who, when you hear people talk about just the great joy of going to a movie and turning your mind off, if you're one of those people who hears that and goes, why would you want to do that? You're in the right place. Because I certainly have never understood that. Why would you want to turn your mind off? Turn your mind on. Just leave it on. And this is and you should all leave your mind on here. Also, this is a very funny movie too, believe it or not. When this film was made in the 80s, there was a general sort of understanding that everyone had the historical literacy and the understanding to know kind of everything that had gone on in the previous 40 or so years. At this point, I don't know if everybody's really so well aware of all that, so I'm just going to give you kind of quick sort of recitation of sort of what happened before this film begins. This film begins with the atomic bomb test in 1945 on the Trinity site in Alamogordo, New Mexico. So prior to all of this, it was only in 1895 that X-rays and radiation were sort of identified and discovered. Fast forward to Leo Szilard, who's a really important figure in all of this, conceiving of the atomic chain reaction and considering the possibility that it could be used for weapons. On up to 1934, when Enrico Fermi splits the uranium nucleus without knowing it. 1938, when Otto Hahn, Otto Frisch, and Lise Meitner knowingly split the uranium nucleus, up to 1939, when Otto Frisch coins the term fission. And 1939 was an extraordinarily eventful year in all of this because Szilard, who was concerned that Germany might well develop that weapon technology that he had conceived of 6 years earlier, and also realizing that the proper uranium, the properly isotoped uranium that could be used for doing this is mostly in the Belgian Congo, goes over to his friend Albert Einstein's house, mainly because Albert Einstein was tight with the royal family of Belgium, to write a letter saying, hey, maybe you should restrict this from these awful German Nazi people who want to come in and get the uranium out of there. And as a sort of side note, the driver who drove him out to Albert Einstein's Long Island estate said, maybe send a letter to the State Department too. So believe it or not, that's kind of how all of this happened. And this became known as the Szilard communication, Szilard letter, the Einstein letter. Went to FDR, starts a long chain reaction that sort of culminates after the Japanese bomb Pearl Harbor with the development of what eventually becomes to become known as the Manhattan Project. And at that point, this film begins. So all of that kind of stuff happens before this film. Now, we have a very special guest, and I gotta say, there is a term used in nuclear war and weaponry called overkill, meaning that you're just putting a way more effective weapon system out there than you need to put out there. We've done that tonight because almost at this point with the technology involved, which is 80-year-old technology, almost any high school science professor could handle this, but we have such an eminent expert here. Dr. John Kilic received his PhD at Harvard, and he did postdoctoral work at Johns Hopkins and Rutgers, then became a faculty member in the theory group at UT, and subsequently a tenured associate professor. His research is focused on extensions of the standard model of physics, which he just helpfully explained to me, with an emphasis on experimental signatures. My doctor has a very experimental signature. Specifically on model building, collider physics, and dark matter searches. It may be reasonably inferred that he is smarter than you are. He's certainly smarter than I am, as you'll note soon. But I will do my best, and I hope you will too, in the discussion that follows this film. So what we're going to do is he's going to come up, just say a couple of words, and then we're going to watch the film, and then afterwards we're going to sit down and have a discussion with this very smart man, my new friend, Dr. John Kilic. Come on up.
Thank you very much, Lars. very happy to be here with you all. And thank you for, Science on Screen to invite me here to give you my 2 cents. I immediately thought this was going to be very interesting. I'm certainly interested in the science that we're going to see, but I also like dark humor, and I thought this was a great combination. Just to tell you a little bit about myself, as you've already heard, I'm a faculty member in the physics department at UT Austin. I've been in Austin since 2011, and I do most of my work, my research on particle physics, trying to understand the world better than we already do, try to fill in some of the gaps that we have in our understanding of the universe. This involves strange sounding things like dark matter, and it's just a lot of fun. It's something that I have fun doing, I feel very honored and privileged to have the kinds of colleagues that I have at UT. It's really, we have a very, very strong physics department, and I think we should all feel good about that. I think we're ready to get this started, and at the end, I'm happy to tell you, we'll have questions and answers, and I'm happy to tell you more about anything that you want to hear connected to the science of this movie.
Excellent. Thank you so much. Thank you, Dr. Coolidge. We'll see you guys in an hour and 36 minutes. Welcoming back to the stage our special guest, John Kilic. Come on up.
Thank you.
Wow. So we could just as easily, we've got an expert here on physics, but we could just as easily have an expert on abnormal human psychology, on philosophy. It all kind of just sort of adds up when we look at this. And kind of what was happening was humanity was being hit with this existential change, that all had everything to do with this sort of I refer to it as the splitting of the atom. I'm probably being a little too elementary when I say this. But what happened to give us this technology? What did scientists figure out that got us to this place?
This was the first half of the 20th century. We were just beginning to understand really the fundamental building blocks that make up matter. Just maybe a 2-minute refresher. We're all made out of atoms. Atoms have what I call nuclei, which are much smaller than the atom itself. Mm-hmm. So for most reactions, what we call chemical reactions, say you buy wood or coal and you burn it, what happens is that the stuff that's on the outside of the atoms, the electrons get reshuffled, and that yields a certain amount of energy. There's a convenient unit of energy called the electron volt. I don't have to go into detail of what it is, but just for comparison, when you have chemical reactions like the burning of something, each atom releases some number of electron volts, say 10 or 100, maybe 1,000 in extreme cases. Now, the nucleus in the middle of the atom is much smaller and packs a lot more energy. If you reshuffle things in the nucleus, which does not happen in chemical reactions, this happens in nuclear reactions, now we're talking about energies released per atom of millions of electron volts. So it's a much more potent form of energy release. In the 30s, 40s, leading up to the building of the atomic bomb, people understood how they could do that, controlled or uncontrolled. Uncontrolled is easier. And by understanding that you can, for certain types of materials like uranium, have one atom not only release that energy, but trigger other atoms, other nuclei around it, go through the same process, which then trigger others around themselves. This is called a chain reaction. You start small and it exponentially builds up. That is the underlying idea behind the original atomic bomb, what we call the fission bomb. Later on, as is called the hydrogen bomb in this film, is a different type of process called fusion, but they both involve rearranging of the building blocks of the nuclei inside of atoms. In the case of the fission bomb, the original atomic bomb, you start with large nuclei that are sort of so large. Nuclei don't like to be that large. They want to split off. So you start with a very large nucleus, uranium or plutonium, and they split off. They release a lot of energy. This is called fission. The fusion bomb is you start with very small nuclei. In the case of hydrogen, it's the smallest one possible. They want to get together, fuse. And, as with any physical system, physical systems like to lower their own energy and in the process release energy to the environment. This is what happens in both types of reactions, fission and fusion. The large nucleus finds a way to exist at a lower energy state by splitting. The very small nuclei find a way to exist in a lower energy state by joining. And in both cases, a very large amount of energy is released. Is that at the level that you were looking for?
And so by putting this together in weapon form, they were able to find a way to sort of trigger, to sort of contain this process, to make it happen in a predictable manner, so that then they could drop it, and then some sort of fuse or something would create this chain reaction, which would then trigger a great amount of energy that would then, I think it would also ignite TNT or some other mechanism that was there with it, I believe.
So the designation of 10 kilotons or 10 megatons is a way to compare the energy release of a bomb to an equivalent amount of TNT. So I believe the majority of nuclear weapons are sort of below the megaton range, but the really big ones can go up to 20 megatons. I think Russia had the record there with about 50 megatons. The H-bomb, the hydrogen bomb, the fusion bomb, is a lot harder to construct. It actually requires the atomic bomb, the fission bomb, to trigger the fusion reaction. So you first explode a little atomic bomb to trigger the fusion bomb, the hydrogen bomb, which is much more powerful.
And how does it do so much damage? Is because of the great energy that's being released?
For the most part, that's really what it is. It's you are releasing a very large amount of energy in a very short amount of time, and that energy will do damage. About half of that damage is just done by the blast. About another half of it is done by the heat released. And as you know, one of the segments of the film was explaining this also, the third one's radiation. The majority of the damage is actually done by the blast and the heat, and they are essentially the same types of elements that are contained in conventional bombs also. Then there is the radiation. Just in terms of pure energy release, it's a relatively small fraction of the full energy release of the bomb. But of course, the effects linger. The blast and the heat, you get it immediately. The radiation can linger, and it's dangerous in its own way, and that's the added element of danger in the case of atomic weapons.
There's a famous moment that happened in history, and I alluded to it a little bit earlier, was just when the scientists who were working on, who had figured out that there was a theoretical possibility of weapon systems evolving, go to Albert Einstein, and he has a famous quote, and he said, "I hadn't considered that." He hadn't considered that it could be used for weaponry, and it's interesting to me as someone who's obviously an eminent scientist in your field. How does it happen that the military or the government, et cetera, becomes all of a sudden super interested in science? And how does that happen? Does it happen through the universities? How does that happen?
I don't think there is a unique answer to that. I think it's very much context dependent. At some point, somebody in the places of power would become aware of an idea that would, allow them to, conduct their own agenda. How that idea gets to them could be something direct, like the letter that Einstein wrote, or it could be scientists that are actually working for the government in a government laboratory in a project that already had a goal of creating some sort of product. But once the science is there, sort of the policymaking decisions are typically not in the hands of the scientists. And so, which I think starting with the Second World War sort of started the scientists to think in ways that they hadn't before of, should I even release this piece of knowledge? I just figured something out. And just in terms of science, of understanding the world better, of understanding truth better, this is a step forward. But what can it be used for? And should I just sit on this because I don't trust the people in power to necessarily use this for good, and it can be used for evil? That's a new one, I think, for scientists.
Yeah, it's really big. An interesting thing happened. This is a field in which many letters were written and signed by many people, but the scientists who worked on the Manhattan Project, a number of them wrote an open letter to the American military saying, please don't use this against Japan without a demonstration. Give them a demonstration first before you use it on them, and so that there are scientists at times must become ethicists, I suppose, rather than just scientists. And I think that it's this kind of conflict that makes that happen. And I'm sure we'll have questions about that when we kick this to the audience. I did want to ask about, they talk a great deal about fallout and so forth. What does that mean that there's radioactive fallout?
Mm-hmm. So in the bomb, there is this material that causes the nuclear reaction. It can be, again, the larger nuclei, smaller nuclei. In any case, that reaction will release radiation in various forms, alpha, beta, or gamma radiation. Gamma will travel the furthest. It can release neutrons. So all of these are tiny particles that can release energy, which can be destructive to living tissue. In a bomb that is exploded, say, several miles in the air, which for a large fraction of nuclear weapons is sort of the most effective way to do it, the radioactive products would be relatively small and distributed in the upper atmosphere. So by the time, they come down to the ground, they're mostly already depleted. They've already gone through the nuclear reaction. But what can happen is the blast can move a lot of dust in the air, or, fires can release a lot of smoke, and the little grains of carbon and water or what have you in the dust and the smoke can capture some of those radioactive elements that would have typically gone through their dangerous phase before settling down, can now come down earlier, having been stuck to the smoke particles or the dust particles. And so now they collect on the ground and release their radioactivity much closer to where the people are. That's typically what is referred to as fallout.
Mm-hmm. And it remains dangerous for until it's depleted.
Correct. And depending on what element you're talking about, that can take different amounts of time. I would think that the majority of the elements that are actually in the atomic bomb go through their reaction relatively quickly.
Yeah.
But there are different bomb types, and some of them may even have materials in them that are designed to be around for longer.
Sure. Are there, I was going to ask what, before we go to the audience for questions, what sort of innovations have happened in the field of nuclear fission or fusion? I don't know if there's innovations in if it's even possible to say that weaponry is an innovation in any way, but do you know if there's been, if the weapons that are out there now are more innovative than the weapons that they had then?
To my knowledge, and I'm not necessarily an expert in this,
of course,
but to my knowledge, the weapons technology matured relatively early on. Mm-hmm. That after the hydrogen bomb, not much has changed in the actual design of the weapons. The science has not changed very much. What has changed is the coordination. For example, once computers became widely available, delivery methods, ICBMs and submarines came later. There were some ideas that came later, like the neutron bomb, which is a type of nuclear device which releases relatively little by way of sort of the actual explosion, the blast and the heat, but releases more radiation,
Right.
so to kill living things without causing a lot of material damage. And it hasn't. There has been a lot of, I believe, popular sort of negative reaction once that came out. So I don't think that idea was ever very popular, and hopefully hasn't been invested in very much. Of course, a lot of things are secrets, so nobody knows. Now, there is also the peaceful side of this, of nuclear energy.
Yes.
And there, in terms of nuclear reactor design, all we're talking about is the fission, the larger nuclei releasing energy. That technology, even though, again, at the core, hasn't changed very much, but better and better, safer reactor designs have come along, even though, of course, the fear of nuclear war has, and the radiation that comes with it, has had a lot of psychological effect, sort of pushing people away from nuclear energy. Actually, considerably, all things considered, it's a relatively safe and carbon-free form of energy, but also it can't power the entire world because there just aren't that many. There isn't enough uranium or other heavy nuclei available to power the world. There is fusion, the reaction that also powers the hydrogen bomb. That's been work in progress for many, many decades. We do not have, even though, the uncontrolled form of fusion, the weapons form, has been around since the 50s, the controlled form of fusion, which, by the way, powers all life on Earth because it's happening in the sun. That's, where all of the energy in the solar system comes from. A human-made controlled fusion reaction that can be sustained and that can deliver energy is still one of the holy grails of, both physics and engineering. It hasn't happened yet. It may happen in decades, but not tomorrow. And there are large international collaborations trying to get us closer to that goal. If and when that happens, it can be one of the big pieces of solving the energy puzzle in the world.
Whoever figures that out will win a nuclear prize and will probably become the richest person outside of the cryptocurrency world. Yes, probably.
I wouldn't be surprised.
Let's see if we've got any questions from our audience. And this can touch on a lot of different areas. So I see a hand right back here.
Sorry, are we talking about the actual, the Manhattan Project and so on that happened back then, or are we talking about a hypothetical future scenario of some new innovation? Back then. I mean, I'm not a historian. I know a little bit about it. I'm happy to tell you what I know. I'm sure there are, many books and other sources out there that can probably give a much more complete answer. But yes, so actually Enrico Fermi, who was an Italian immigrant, who was one of the leading physicists in the early 20th century, played a very big role in the understanding of nuclear reactions. But because he was not a U.S. citizen, they essentially didn't trust him to lead that project. They picked Robert Oppenheimer, but actually sort of behind the curtains, Fermi was still playing a very large role, among other things, directing the effort that produced the fuel or the materials that eventually were used in the bomb. But then also this, very select brain team of scientists were recruited to work in the Nevada desert. Among them, many names have become prominent later on through research that is not linked to weapons development. And you just had this team of people there. And my understanding is, to a big part, their motivation was, if we don't do this, the Germans will. because at the time that was the main fear, less so for Japan, more for Germany. But of course, even after Germany surrendered, which was sort of the information at the very, very beginning of the film, the effort, I think at that point, had enough inertia that it could not be stopped, and the bomb was created, and the politicians decided to use this in the Pacific Theater, even though that sort of really was not, I think, what the majority of the scientists in the Manhattan Project originally set out to do. They were just trying to produce the capability before Germany had it.
Yeah, and there were other scientists like Otto Frisch and Otto Hahn who had come from Austria or Germany and were did not want to support Hitler. Some of them were Jewish, some of them had Jewish relatives, some of them were just humane people who left and decided to help work with the British or work with the Americans to help develop this technology. It must have been an amazing conundrum, like an amazing moral dilemma for those scientists to have to bring something so destructive to life. Because America, even though they were the good guys, as you can see, we're idiots. We're primitive. Humanity was primitive, and to have to bring these sort of horrible things to life must have been an incredible dilemma, really.
And we can all debate, I guess, when we're lying awake at night, are we any less primitive today?
Absolutely. Just this is 70 years ago. Most of this stuff, this is really not that long ago. If anything, we're a little bit better at telling lies to ourselves, than we were then. It's a little transparent when you see the propaganda. I wonder if we have any other contributions right over here. Yeah.
I don't have the numbers at my fingertip. I'm pretty sure it did not rise up to the 100,000 range, but it is true a lot of radioactive material was released in the above ground tests, which after a certain point, there was an international treaty to not do that anymore. All tests after that were conducted underground and leakage was minimized. But I do know that scientists, especially who want to do things like radioactive dating of materials, you see it in the records. I mean, you see the sort of the historical record, and it's a very small number in the 1940s, goes up, and then sort of continues at that level because of all the radioactivity that was released in just the span of a few years where above ground tests were conducted. So the problem is, any given amount of radioactivity raises your probability of developing cancer by a certain amount. The amount is not as large as most people think. It's actually a relatively small increase. However, the problem is, when somebody does develop cancer, it's it is impossible to know, would you have had the disease without the radioactivity, or was it just that little added amount that, caused your particular illness? And psychologically, I believe most, we are all primed to think that, if you can think of a cause, that must be it. And so, even though, around the natural world around us also contains a good deal of radioactivity, it's very easy to think that anything that bad that happens to us happened because of mistakes that were made by other people, such as nuclear testing. I hope none of this sounds like I'm supporting nuclear weapons development. I would much rather live in a world where there are no nuclear weapons at all. But there is a psychological effect of thinking that the effects are far larger than they actually may be. Again, I think that the 100,000 is too large a number to correspond to truth.
Yeah, it's funny. There's a whole market in the world of salvage. I'm sure you all read all the salvage journals, as do I. But for steel that was manufactured before the Trinity tests, so pre-atomic steel or whatever they call it, because otherwise every bit of steel that's ever been manufactured has a certain amount of radioactivity that imbalances measurements or whatever. So I find that fascinating. I don't know why you'd ever need pre-atomic steel, but if you find like a ship that was manufactured prior to World War II, apparently that steel's worth a lot of money.
I can believe that.
Yeah.
And you know, it's another one of these psychological effects that we think the world is so large. How can we ever change something, you know, some fundamental property of the world? Right. And this is true for, you know, radioactive testing. It's true for, you know, the climate. Now, again, people find it hard to believe that anything we do could change the climate of the entire world. And I don't know. I guess we will all need to come to grips with our psychology over some amount of time.
It's like one big cell, isn't it? You know, it really is. That's a heavy concept, I guess.
It's a closed system.
Yeah. Right over here, yeah.
It feels like in wake of Hiroshima and Nagasaki, they would have a lot of data as to how atomic energy affects people. So how much of the propaganda of the 50s was just the government trying to do the keep calm thing, or were scientists legitimately still figuring out the effects and that information wasn't as readily available?
I'm sure the information was not readily available. It was, I think, still very, very secret. Still is, most of it. But, you know, that said, I'm fairly sure that they did collect lots of data in terms of the, you know, potential destruction, power of destruction, and so forth of atomic weapons. I'm not quite sure if I've answered the question correctly, so please.
You know, the whole duck and cover thing, and how we all laugh and all that stuff.
Right. So I think in a lot of these things that we laugh at, there's also a bit of loss of context. So I don't think the duck and cover was ever proposed to shield you from the blast itself. That's ludicrous. It's more that, you know, if you're sufficiently far away to, you know, not the building that you live in not be completely leveled when the blast happens, there may still be flying glass fragments and other things, and you know, you have a better chance of not being injured when you duck under something. It's not meant to protect you from the fireball. It's meant to protect you from, you know, less destructive forms of the aftermath. But anyway, I think there was a logic behind a lot of these things, and it's easy to sort of see them out of context and laugh at them. But I mean, at the end of the day, if you happen to be within the lethal blast radius, you know, nothing is really going to protect you. Not a fallout shelter, not duck and cover, none of it. You know, just there's a big area where nothing is going to survive.
To just kind of seize on one part of that, they did really set up Hiroshima and Nagasaki because they wanted to do it in cities that hadn't been bombed. They really did set it up almost as a test site. And it made me wonder that when there's the thing that happened in Bikini where it's like, the wind shifted and the fallout blew into this other adjoining island atoll, that almost to my paranoid worldview sort of sounds like that's an experiment on those people who are then being hit with that fallout. And then later on, when it blows into that town, the wind shifted again. Look, the wind keeps shifting. It almost, to me, does look like a human experiment.
And a very reckless one.
Yeah, of course.
And a very badly, I mean, I don't know if they were thinking of it as an experiment. I mean, they certainly were thinking of it as an experiment of nuclear weaponry,
sure,
but they were not thinking of it necessarily as an experiment on human beings. But they should have, and they've taken far too few precautions. I mean, the wind does shift, and
It'll happen.
the fact that you don't think about that before you explode a 10 megaton bomb doesn't say a lot of good things about you.
or about how you value the lives of the people who live in that area.
Exactly. Exactly. I mean, there are, also aspects of it of, how much do you value the lives of people of other nations versus people in your own nation. Yes.
There's colonial aspects, master race aspects of the whole thing too that are disturbing. I wonder if we have, right over here. Please.
I'm curious, kind of bringing it to the now and all the research that you're doing, the reading I'm sure you're doing in physics. Are there things that concern you currently? Research that give you a little bit of pause or.
Great question. So let me start by a quote. I believe this was delivered by a mathematician with the name of Hardy, or I think either in the late 19th century or early 20th. I may be wrong. And it was a mathematics conference, and he raised a toast and said, "Here's to pure mathematics. May it be of no practical use to anybody ever." And especially, I think, after the Second World War, a lot of physicists sort of maybe had internally the same wish that, whatever they did, that it remain as pure science and not be used for any evil purpose. My research, actually, particle physics, really kind of finds itself in that position. I actually, before I was a faculty member at UT, I was a postdoctoral fellow, and one of my supervisors at the time posed us a challenge of take the model of the world as we know it as particle physicists. And, we understand quite a good deal about the world. We understand many of the fundamental interactions that govern how the world works and the microscopic particles. And the challenge was, don't change anything about what we understand, but we know that what we know is not the full story, so more will be added. So add your favorite thing, whatever it is, to the amount that we already know for sure, in such a way that it will make a difference in everyday life for the people who are not scientists. And to my knowledge, nobody's really risen to that challenge because the things that do affect us, like nuclear energy and so forth, that was already figured out a long time ago. All of that is established knowledge. But the things I'm working on now and my colleagues are working on now are very unlikely to ever be used in an everyday context of, either building bombs or for good purposes. For example, dark matter or the Higgs particle or, any of these things are very unlikely to have technological consequences that will affect my life or any of our lives. Just as a point of reference, consider the theory of relativity, right? It was developed over 100 years ago by Albert Einstein, and we've all heard of it. I doubt there's anybody in this room who hasn't heard of the theory of relativity. But if I ask you, how has the theory of relativity affected your life directly? I would imagine that's a challenge to most of you to even come up with anything. It's actually a challenge to me. And I can give you one answer. It's kind of a cop-out answer. For example, people will tell you that GPS, the positioning system, is so accurate that without having the theory of relativity, it would be much less accurate. But, when we talk about the theory of relativity, GPS is not the thing that comes to your mind first, right? You'd think about space and time being curved and black holes and all that. And yet none of it has really ever played a role in our lives in some technological way. Nevertheless, it sort of tells you that science can be very important and very pervasive in a cultural way, even without the direct technological applications. That was certainly true for relativity and some fundamental truth that a particle physicist, not necessarily me, many of my colleagues, one of them might discover, may pervade our culture in an equally powerful way without having a direct technological application.
And this gets to the point that you've swerved over into a slightly different lane for this discussion, which I really appreciate. But when you were with us before, it was for a film called Particle Fever, which is much more directly in your lane of what you do. And I can't recall if anybody, that's been a few years, I can't recall if anybody asked you, give us the inside scoop. Is one of these super colliders, is this going to destroy reality? Because we need to know. We'd like to prepare.
I mean, maybe certain aspects of reality we could do better without. And that said, no.
Yeah, okay.
The answer is no. I can go at this from 10 different angles. I mean, one thing I'll say, which hopefully will put your mind at rest, is far more violent things happen in nature than in any human-made experiment, including the super colliders. For example, very energetic cosmic rays bombard the Earth, and they usually don't get much further than the top of the atmosphere where they just collide with stuff. But if powerful particle collisions could cause black holes that would eat up the entire Earth, it would have happened long before humans ever evolved, because those cosmic rays keep coming at us. So believe me when I say that the people who design experiments like the Large Hadron Collider or other particle physics experiments do spend time thinking about, is this going to do something that has never happened before, and what could the consequences be? When the Large Hadron Collider was just turning on, there was a humorous website where you could go and click on, has the Large Hadron Collider destroyed the world yet? And you would click on it, and it would say no. No. I mean, knowing the science, I have zero worries about, the Large Hadron Collider destroying the Earth. There are many other things that I'm worried about that we all do that could destroy the Earth, but not the Large Hadron Collider, and not any of the particle physics science that people are working on.
Okay, we'll hold you to that. So please don't destroy the Earth if you don't mind, or at least give me a couple weeks notice.
I'll do my best.
So I can clear up those credit cards. Maybe we have one last question from our audience. I see a hand right back here. I saw you earlier.
My understanding is that during the Manhattan Project, when they were building the very first bomb, a few people raised that concern, that not about the ocean or the bottom of the ocean, but the atmosphere actually catching fire. As far as I know, they pretty quickly convinced themselves that it wasn't going to happen, but then it sort of entered a type of dark humor that pervaded the whole project, and people would keep joking about it, bringing it back up, even though I think at that point they all pretty much knew it wasn't going to happen. Again, I think this probably says more about human psychology than actual nuclear physics. But no, by the time the bombs were manufactured and used, I don't think anybody was worried about that anymore.
That military guy did a terrible job of reassuring people, by the way, because he's saying, like, it was so needlessly specific. Like, if I went to dinner with you and I was like, I'm not going to kill you and eat your pancreas, you'd worry a little bit that I was going to kill you and eat your pancreas because I was so specific about it. It was a very, very weird message that guy had, I thought. But we saw a lot of very strange messages. So give us a ray of hope in our future with something that we can expect from science that's gonna make everything better.
I think, we've seen some really terrible things that can occur when people put their minds to it, and science certainly has played its role in that. But there are, I think, very worthy goal of scientists still to pursue, developing controlled fusion and solving the energy problem of the world, coming up with sustainable renewable energy that can be stored and distributed. Those are all big challenges, both for science and for engineering. And at UT, I constantly interact with our students, and I am encouraged as I see them. These young people who are not yet as cynical as I am, and they have hope for the future, and they're full of energy, and they have all the right goals, and they have the work ethic, they have the intelligence, and yes, I think they will change the world for the better.
That's a great note to end on. Let's hope so. I really appreciate you being here,
Thank you
Dr.
so
Kilic.
much.
And thanks to all of you for being here and asking such great questions.
Thank
We
you.
really appreciate it.